Hello, everyone. My name is Carolina, and I'm a PhD student at Rutgers University. Today, I will be talking to you about private multi-group aggregation, which is joint work with Rafael de Oliveira and Selim El-Wahid. Private aggregation has received attention in the literature and has applications to federated learning and general population statistics. And the main idea is that there's a server that wishes to compute the sum of values held by multiple users. These values can be anything from votes by the users or maybe gradients, like in federated learning. The users want to share their values with the server. However, they worry about their privacy, meaning they want to keep their values hidden from the server. This setting has been looked at in the literature, and I apologize that this is by no means a comprehensive list of publications, but the main idea is that the users report or push noisy versions of their value, and this noise averages or cancels out when the values are added at the server. Now, in many applications, users can belong to different groups based on their race, age, or political views, to name a few. And the server wants a finer aggregate of the population. So wants the aggregate not over the whole population, but the aggregate for each group separately. This led us to define this variation on the traditional aggregation problem, which we call private multi-group aggregation. In this setting, we consider, in addition to holding a value, each user belongs to a different group. In this figure, we show 3 groups represented in blue, green, and red, and in general, we can have any number of groups. And here, the server wants to find 3 aggregates corresponding to the 3 groups. This setting can have many applications. For example, consider primary elections, where there are 2 groups, Democrats and Republicans. Each user's value is a vote to his preferred candidate in his political party or group. So the server's goal is to tally the votes per party and find the winning candidate in each group. Another example is vaccine or drug trials. So a medical research group wants to test the effect of a new vaccine on patients with or without diabetes. Participants want to contribute their vaccine test results, or in other words, their values. However, they worry about revealing their diabetic medical condition. Now, these are only some examples, and there could be many more. But to summarize, the key idea here is that the user belongs to a group which he wants to keep private from the server. Now let me be a little bit more precise. In our setting, there are n users that communicate with a single server. Each user belongs to one of k groups and also holds an integer value. The user knows his group and value, but the server does not. Our goal is to design schemes that allow the server to find an estimate of the sum of values per group. So the server ends up with a vector S of estimated sums. For a scheme, we care about 3 things: communication cost, utility, and privacy. We determine the communication cost by the total number of bits communicated by all the users to the server. As for utility, it's the MSE. So let S hat be the server's estimate of the true sum S. Then to find the risk of the estimator, we look at the normalized mean squared error. The third metric we consider is privacy. Like we said before, we care about keeping the user's group private. And to measure the privacy level guaranteed by a scheme, we use local differential privacy. So we want a scheme to be epsilon locally differentially private for a given epsilon. And for this setting, we propose a new interactive scheme, which we call the query and aggregate scheme, or for short, Q&A. The novelty of the Q&A scheme is that, as its name suggests, it's a pull scheme, where the server queries the users and then aggregates their answers. This is the novelty compared to existing private aggregation solutions, even for a single pool. So the user answers an assigned query instead of just reporting a noisy answer. An important feature of our scheme is that the assigned queries are completely independent of the user's values and groups. This is powerful because it means that the queries can be assigned as part of the scheme agreement, or they can be done at off-peak times, which allows a reduction in the communication cost. We completely characterize the scheme's performance in terms of communication cost, privacy, and utility. And what's interesting is that the communication cost is independent of the number of groups K. And this scheme incurs cost and utility. However, the normalized mean square error goes to zero as the number of users increases. In this graph on the right, we compare Q&A scheme to a scheme we call randomized group. The randomized group scheme is an extension of methods in the literature, mainly randomized response, and it does not include a query stage. Instead, the user reports a noisy version of his group and value. The randomized group scheme here is represented in green, and the Q&A scheme is represented in blue. And as you can see, the Q&A scheme does well in terms of utility versus privacy in the high privacy regime, or when epsilon is small. You can find more details about this comparison in our paper, but the takeaway message is that our query-based scheme can perform better than just reporting a noisy version of the user's group and value, at least in the high privacy regime. Now, to explain the steps of our scheme, I will focus on the case of two groups and two values, and the user can have one of two values, +1 or -1. As a reminder here, the groups can be, for instance, Democrats versus Republicans, and you can think of the values here as votes. The first step of the scheme is composed of the user mapping his group and value to one of the 4 points here in this figure. The x-axis corresponds to group 1, and the y-axis corresponds to group 2. And for instance, if a user is in group 1 and has value +1, he maps his answer to this point here. Then the user is assigned one of two queries, query A or query B. And the query is a question to the user, and here we represent this question by a directed line. And you can see the query splits the plane in half. The user is assigned one of these two queries uniformly at random and independent of his group and value. This query method is agreed upon between the server and the user, so both of them know the user's assigned query. The user answers this query with a single bit. He tells the server whether his mapping is to the left or to the right of the query or the directed line. So the user has essentially compressed the information about both his group and his value into a single bit. Another important thing to notice here is about privacy. When the server receives an answer, it corresponds to a region of two possible mappings. The server cannot determine with certainty whether the user belongs to group 1 or to group 2. And notice that these queries are assigned independent of the user's group and value, so they can be assigned in an offline phase before the start of the whole process or as part of the scheme agreement. So there could be two phases, an offline phase where the user is assigned one of these queries, and an online phase where he does the mapping and sends the server an answer. Now that the server received the answer, let's talk about how he interprets it. Since the server knows the user's assigned query and he knows his answer, based on this figure over here, he interprets this answer as a two-dimensional vector, where the first coordinate corresponds to group 1 and the second coordinate corresponds to group 2. Here we show how all possible answers are interpreted, and notice that they all have two important properties. The coordinate corresponding to the user's group always has the correct value. And the other coordinate is uniformly random value +1 or -1. And this follows from how the queries were designed and assigned with equal probability. Finally, after receiving all the answers from all the users, the server sums the interpreted vectors to find the estimate of the two sums. Finally, to summarize, we've introduced an interactive query and aggregate scheme. In this scheme, users are assigned queries in an offline phase. This allows for a reduction in the communication cost such that the user sends 1 bit for the case of two groups and two values. There was no addition of direct noise to hide the user's group. Instead, we leveraged the randomness of the user's values in addition to smart queries. For more details about our work, I invite you to visit us during the poster session. And thank you everyone for listening, and have a good day.